Okay, so here's a overview of one of the problems that a lot of people had trouble with on the photoelectric effect. Uh, just a image here to start with. Um, Again, remember that one of the key ideas in the photoelectric effect is this idea that depending on the wavelength, we'll get electrons ejected or not. So you can see over here with 700 nanometer light of a long wavelength or low energy, we don't have enough energy to eject electrons. 618 nanometers is just enough energy to start ejecting electrons, but the ejected electrons are moving very slowly. And then if we go down to 400 nanometer light, much higher frequency, the ejected electrons have much more energy and are able to move away from the metal surface very, very quickly. Again, that same idea is sort of shown graphically back here in this slide, right, where depending on the frequency, we get electrons ejected or not. And again, the kinetic energy of the ejected electrons is what changes with frequency here. This key cutoff point is something you've got to be able to identify from the given context of the problem. This is the frequency of light where we first start ejecting electrons from the metal. Remember, that's called threshold frequency. And again, the way this works is, again, we use sort of our properties of light here and have this sort of key slide that explains what's going on in terms of conservation of energy before and after an electron might be ejected. Photon comes in with an energy given by h nu. Then if it has enough energy, it's going to be able to absorb the photon and eject the electron. The ejected electron, again, the equations here, W is, again, that binding energy or threshold energy of the metal, the energy holding the electron into the metal in the first place, and then the kinetic energy of the electron, how fast it's moving after it gets ejected. Yeah, really important in these problems just to be clear on what is a property of the metal, which is the threshold energy, threshold frequency. Again, we could also think about a threshold wavelength. There was a problem there on the homework asking about the threshold wavelength, right? The threshold wavelength is perfectly fine to talk about because if we know the threshold energy or frequency, we can just use these two key equations to get from, again, if I have the threshold frequency, I can use this equation to solve for threshold wavelength. If I have the threshold energy, because it is a photon that's coming in, we can use this equation to get the threshold frequency or to get the threshold wavelength from the threshold energy. So, yeah, really the biggest thing is just keeping each term in this equation in the proper place. Again, remember conceptually, the key idea is down here. This is sort of why, I don't know, all this text is here, is to just help you remember that key information. That if the photon's energy is too small, right, because energy is proportional to frequency, that energy too small means the frequency of the photon is less than the threshold frequency, then we don't eject an electron. Again, one helper there is that the kinetic energy can't be negative. And then again, if we have enough energy, we're going to start ejecting electrons, and we can just use this equation. And since the kinetic energy is over here, if we subtract W from both sides, we get that the kinetic energy of the electron is the energy of the photon minus W. And yeah, again, the threshold frequency and binding energy depending on the metal, W is h nu photon, and again, if you wanted to do this in one step, we could also say that that's hc over, So yeah, W is h nu naught. That's a typo on there. But yeah, W is h nu naught. Again, we can see that equality right there in that equation. And again, that would also be hc over lambda naught if we had that. Okay, with that out of the way, let's look at Einstein's photoelectric effect. This is problem 6 from active. So in this case, they're going to give us the threshold energy. Again, one thing you need to do with that, right? What is that threshold energy? Well, again, you need to know that the threshold energy is, again, it's the property of the metal cobalt. That's our W. Ultraviolet light, right? This is basically the photon or light that's coming in. Kinetic energy, right? That's going to be kinetic energy of the electron that we want to solve for. And again, we have two versions of the equation for the photoelectric effect from our previous equation sheet. E photon is W plus Ke electron, or this version down here. Since we're given W, maybe it's easiest to just use this top version of the equation. E photon is W plus kinetic energy of the electron. Again, we're given W, we're solving for Ke. Energy of the photon we weren't given, but in all of these problems, you always have to just have ready to go the relationships for light on its own. C is nu lambda, and E is H nu is Hc over lambda. So because we were given the wavelength lambda of that photon, we can get the energy of the photon. So maybe we'll do that as a first step. E photon equals Hc over lambda. Now, once we use this to go from wavelength to energy, then we'll just be able to plug back into this equation to solve for kinetic energy. Again, we've got nanometers there. Nano means 10 to the minus 9. So 30.5 times 10 to the minus 9 meters. Again, really important in this part of the class to just be very careful with your units and make sure you're using them properly. Active will normally include the units for you, but you want to, on the quiz and exam, do the units all yourself. In this case, it'll all work out here. Meters will cancel, seconds will cancel, and we'll just be left with, again, it's an energy, so we need to be in joules, which we are. Then solving there, 6.63 e minus 34 times 38 over 30.5 e minus 9 gives us 6.52 times 10 to the negative 18 joules. And again, that's pretty typical, 10 to the 18, 10 to the minus 18, 10 to the minus 19 for energies. Now that we have the energy of the photon, now we're ready to plug in, because again, we now know the energy of the photon. We now know, or we were given right away, the threshold energy. And the only unknown is kinetic energy of the electron. So again, using that equation, we can take this and just subtract W from both sides to get kinetic energy by itself. We don't need to do any dividing here because we're adding two things over there. So we get E photon minus W is equal to the kinetic energy of the electron. The energy of the photon we just solved for, 6.52 times 10 to the minus 18 joules minus 8.01 times 10 to the minus 19 joules. And that gives us 5.7. How many sig figs do we get? We do get 3 here. We've got 3 and everything else. So 5.72 times 10 to the minus 18 joules. So yeah, the actual math is not, there's not too much math here, just remembering your algebra. In this case, subtracting W from both sides. But yeah, you are always able, and you need to be ready to go back and forth between energy, frequency, and wavelength sort of automatically, because we can always give you any one of those variables and have you determine the other two. So yeah, that's one of our example problems again. Let me know if you've got any questions, send an email, or stop by office hours. Always happy to help.